Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
This is Enrico Belmonte.
Hey, Enrico. Good to hear from you again. We were, I was mentioning that I'm going to be a bit tired today because of the windy and rainy last night. And when it makes a lot of noise out there, I don't like it. But it also reminded me of years and years ago, the team I was working with had to figure out how to measure the noise that a printer was making. And it was the sound power wasn't good enough. So we just put a microphone there and measured, how loud it was. That didn't get to the gist of what they wanted to test. They wanted to know if it sounded okay, sounded pleasant. And it was kind of vague how they define. It has to, which ones, they had like 5 or 6 printers from different vendors. And they said, which one sounds the best? And I'm glad I'm not designing that test.
I hope that the noise that you heard yesterday was not like that one from the printers, wasn't it?
Yeah, no, I didn't hear any crashing and banging with the printers. There was one of them that was just screeching. It's sort of like, I don't know, you might not be old enough, Enrico, but when somebody puts their fingernails on a chalkboard and scrapes down, it makes a screechy.
Okay, the same noise. Okay.
Yeah, it made that kind of stuff. And then when it would put the carriage all the way to the home position, it would basically crash metal on metal. You hear this crash, and it was like, well, that just sounds evil. That was the low bar for the worst one, but every other, but it was, I don't remember exactly why they wanted to do that. They thought it had something to do with, if it was mechanically engineered correctly, they wanted to get it to be like a Mercedes door close, as opposed to a Yugo door close, kind of thing. And I thought, wow, okay, that's interesting, but I have no idea how you do that. I'll go over here and run an accelerated life test,
Exactly. This is more for noise, vibration, harshness, guys, or NVH. So let's focus on. I think testing is a good topic, and reliability testing is a great topic.
Well, I think the first part, though, Enrico, is what do you mean? Because when I was looking at that test, I wasn't directly involved in it, but I was looking at it going, as this thing ages, as we use it longer, how does the sound change? Does it cross some barrier that says now it's too loud or it's too noisy or too evil sounding or whatever? But I look at it as just the testing in general is, I was going to back up a little bit, is saying, well, what testing is reliability testing? Because I've run into environmental testing. Some teams were doing regulatory testing. Some teams were doing, accelerated life or life testing or things like that. And then some teams were doing control charts with vendors and stuff to see if they were making a product in a stable manner, because if it was out of spec, then it would cause failures. And it was under the reliability team they did that. So how do you define what's reliability testing?
Yeah, to my opinion, reliability test is a test where you observe something that is degrading over time. Okay, so reliability is function over time. So testing for reliability is to monitor that this function doesn't exceed a certain threshold. For example, the noise.
Yeah.
So
no, I get that.
That's my definition. Yeah.
Yeah. I often somebody asked me the other day, is reliability a part of quality? Or I said, quality only goes so far, and we take it over the life of the product. So reliability is quality over time. And so yet we kind of many organizations separate the quality testing from the reliability testing. And I find that there's some redundancy in that. And I often leveraged whatever they were doing and just ran it longer to look at degradation. It was what happens when these parts get old, that kind of stuff.
Yeah, I think there is another differentiation between reliability and quality testing. So generally, reliability testing should be done before SOP, or let's say in the first phase of the product development, whereas the quality tests are carried out when the process is established. So I would make this difference.
Yeah, yeah. And
Yeah.
I found some quality teams like at the last set of prototypes before they go to production, or when we first run protos on the production line, and some organizations would do that to make sure they're ready to go to production and mass production. Then they do all the quality tests. Is it the right color? Does it have the right features and functions? Is it way within the spec? And it's all specification test tech
Yeah.
checking. I don't think it's so much testing as it is. But I did run into one, and sometimes they get all wrapped around the axle around, um, and I'm saying they as meaning the great evil horde of quality folks, just being facetious here. But it's the printer I was working with, the same one that had the sound thing. One of the specifications is that it would print, I don't know, it was like 5 pages a minute or whatever it was in it, and so they and it would print um, something like so many thousands of pages per um, ink cartridge or whatever. They had some specification for how much ink would print certain things, and they ended up just hardcore pushing the print button as fast as they could. They had some software that this thing just printed and printed and printed and printed and printed. And the range of types of tests that they set up and ran to check the functionality were sometimes sped up because they were just trying to count how many pages came out per minute, kind of thing. And then they completely missed a latent defect in the product. And I know I've talked about it on the show before, but there's a little roller in the paper tray that is called a pick roller. It's a little piece of polymer or rubber, and it's just tacky enough that it'll catch the top page and put it into the
Hmm.
mechanism, right? And if it does it right, it's one page and it's off and running. If it slips, if it's too slick, then
Yeah.
it just rolls. And so when they were testing very, very fast, the actual mechanism never made the roller slick because it was just wearing it off as fast as it was accumulating. It was this blooming of some chemical in that polymer. And when we did it really, really slow, it, they only tested did it print 5 pages in a minute. Well, the printer was brand new then. And it took about 2 months for that polymer stuff to get slick. And so the hard part is with quality, and in my mind, it differentiates quality from reliability, is they're testing to specification. Does it do what it's supposed to do? Does the machine do what it's supposed to do? Does the process do what it's supposed to do? Whereas reliability, we often are looking for what don't we know? How could it fail? So doing FMEAs and stuff like that give us indications of where to go look. And sometimes we just need to know, will this last 5 years? And then we go do that. But we're also doing stuff like HALT, where we're looking for, well, how does it fail? What could go wrong?
Yeah, that's a good perspective, Fred. Honestly, I didn't thought in these terms. Yeah, but so I agree with you that when we test for reliability, we should always have the damage mechanism in mind, right? This is, let's say, um, the uh, the aspect that is common to all the reliability test procedure and test strategy. We should
Yeah, no, I agree
we
with
we
that.
we, we
Yeah.
plan. Yeah,
Yeah, I think the more we understand the mechanisms of what can fail, or what is the life limiting aspect of it, or what is the wear patterns or whatever,
yeah,
it allows us to be sure that we are monitoring for that. And I'm quite sure there are, and I've run into this where you're running a test to check one aspect of your product and something else fails. And for me, that's gold.
Yeah,
It's
that's of course that's a great information because you get, let's say, another level of information that is added to your knowledge about the product. Yeah, but what
yeah.
about Fred? If nothing, of course. Okay, so if you test, for example, you say, okay, I need to test this component, and I calculate that the service time will be, I don't know, X hours or X years, and I test it and nothing happens. And not just in the first generation. Yeah, anything doesn't happen in when you test. How
Hmm.
do you deal with that? Because without
Yeah.
generating any failure is quite boring activity, and in the long time it will be seen like waste of time while you're doing that.
Well, yeah, there is. I'm definitely not a big advocate of test to pass. And I mean, there is the zero failure binomial equation that
Yeah,
says, if you got 8 units and they last for so many cycles and you get certain confidence, you can say it's at least this reliable. And it's economical overall, because if you're looking for a small failure rate and you want to test till you get failures to in that, I think the hazard is that if you expected failures and none happens, did you apply the appropriate stresses? Do you have the right interactions and environment that would induce the failures that you were expecting? And if you get no failures, you don't know, whatever. Now, if you have a well established, let's say, a wear mechanism, and you can measure the amount of wear, then you can use other techniques to say, yes, we're exercising it correctly, yet the wear is slower than we expected, and then we had no failures. But unless you have that level of detail, a test to pass, and a lot of industry standards do this, is usually very risky. Is that, do you have the right test? And I've run into so many people that, in I'm going to touch on the quality folks again, um, is that they'll run a test and they're limited on samples and budget and everything else. So they'll run a test to pass. And then it's like, what are you going to do with those samples after that? And, oh, you can have them if you want. I just keep the test running, until I get a failure if I have enough time. And if the failure is completely out of rate, out of whack with what they were expecting, I have evidence that their test may not have been appropriate. But it goes
yeah.
back to the failure mechanisms. This is one of the things you mentioned just a moment ago.
Yeah, but I would like to discuss with you about the following scenario. No, if you have a product with some electronics, and
Mm-hmm.
you know that the weak part consists of mechanics,
Mm-hmm.
but you still need to verify the reliability of the power board or the user interface or whatever you have,
Mm-hmm.
right? And you might want to apply a test to failure for the power board or for the electronics, but you need to really to stay focused on the damage mechanism of one particular component, like say capacitor or
Right.
HBT or something like that.
Right.
Yeah, which is quite no sense, because if you just focus on one component, then you can test the component itself without
Right.
testing the board, right?
Right. Well, one of the things that I ran into years ago is that when you're like, when you suspect that it's the capacitor, and a client told me this one time, is that, is it the capacitor's fault? Is that really your weakest link on that board? Or is it what takes the brunt of the damage because something else, say a regulator, is giving it a peak current that's too much, or peak voltage that's too much for the capacitor? That's, it's not in the circuit analysis, but it's the way that other component behaves that causes the capacitor to fail. And that's where it gets tricky, right? Is how, when do you go to component level testing versus going to the subsystem level testing? And so in that scenario, I was like, you got to be careful when you jump to
Yeah,
components.
yeah, that's another important point. You're saying, hey, if you test the component itself, you might miss how the component is subjected to a certain load.
Right.
You are not reproducing the certain load. Yeah,
Right.
that's also an important step when you're moving from component test to sub-assembly, let's say, step
Yep.
from the capacitor to the power board. But
Yep.
what about the scenario in that I mentioned before, where the mechanics is the weak part, but you have a power board which is designed for function, but the design guideline for function are automatically comprehending the reliability.
Hmm. Hmm.
So you have no problem at all. Yeah. What would you do? Would you test the power board, or would you say no? I don't test it at all.
Well, it starts with who needs to know? And is there a major
The
decision?
project,
No,
your
the project.
project.
But if the project's going to say, if that power board has any risk, we need to test it to find out if it's going to survive or not. Then, and if we doesn't, then we have to redesign or buy a different vendor's system or whatever. But if it's, you've got 20 other things that are higher risk or more uncertain, go do those 20 things. If it's in the top three and it's critical to the path of development of the program, and the program needs to know, is this good or not, then test it. I ran in one. I was working. I was a consultant for a company, and they were making gaming systems, and I was working on the controller. I was working directly with the team that
Yeah.
made the game controller thingy. And I got so many stories about testing with these guys. But um, the console lead engineer for the reliability program had just gotten hired about a month prior, and he came storming into my office, shoulders back, chin out, all this other happy stuff. And he said, "You need to test your." We had a little board that would catch the Bluetooth signal from the game controller or whatever technology they were using, and it would read that signal and send it off to the rest of the machine to
Yeah.
say, "Yeah, turn left or shoot right," stuff like that. It was the exact same circuit board that had been on like the last three generations of the product. It
Yeah.
and it had never had a recorded failure. And he had an allocation map that laid out that to that component, I need to prove through testing, it was only allowed to be through testing, is his opinion, that it was 99 point, and I think it was 8 nines.
Mm-hmm.
And I and
Yeah.
I know that they were having major reliability problems with other parts of the system of this new design. And I said, "You realize that I'm going to have to test over 200,000 components to have a 60% confidence that it's even close to your requirement." "No,
Yeah.
no, no, you got to do it to this, to 90% confidence." And I walked over to his boss and said, "No way. Here's the
No,
field data.
impossible.
You know, you're going to give me $2 million to go test this. I'll happily go test it. But I don't think you're going to give me $2 million to go do this,
Yeah.
because it's pointless. We don't need to know this."
So in this case, you would said, based on the field data that I have collected over time, I would propose to avoid testing completely.
Yeah.
Yeah.
And this guy, though, was hardcore. You test every subsystem, every component, and he had an apportionment laid out. And it was going to cost millions and millions of dollars to do this stuff. And I like, how about you spend that money and get this and this and this part of your system actually working more than 20
Yeah.
minutes rather than worry about stuff that is has never failed, has not caused problems, is robust and proven. And he would not buy that. So I had to go over his head, and his boss was like, "Well, can't you just do it?" And I had that prepared. I said, "It will, in order to do this with the minimum requirements he's requiring, I will need something like 600,000 units and test them to failure to know
Yeah.
to get it." He says, "Do you have the budget and room to do that?" No, let me go talk to him.
Yeah, I think this is where statistics, and so the little statistics behind the success run test is helpful, because it points out how many samples you need for verifying kind of reliability target that you mentioned. Yeah.
Yeah, yeah,
However, I think that the problem is still there. I mean, if if you have a product and you have, let's say, a relevant subcomponent which is unlikely to fail. But I would say if I were the management, I would like a sort of evidence that uh, the this component or the subsystem is going to fulfill a reliability requirement.
yeah,
You need a certain confirmation by
yeah.
your engineering team,
Well,
don't
I,
you?
I agree. Yeah, there is a gray area where you just don't have time and budget to, if I just, and I've heard this, and I'm sure you've run into people that say, well, we'll just throw a few in a chamber and see what happens,
Yeah, yeah,
and heat them up a little bit and see if they're okay. It says the chance of you actually finding any evidence whatsoever that with a, relatively benign test that it's not going to, that it has a problem is very, very, very low. Let's say it has a 5% defect rate on that board, and I only put 3 units by random sampling into a chamber that heats it up to 40C for a couple of days. Well, what failure mechanism are you looking for? What does that
yeah,
temperature actually do? Two, how long does it take for that failure mechanism at that temperature to actually occur? And you're ignoring engineering judgment, and that we've used the same technology for the last 3 generations, and engineering, our FMEAs and all our risk analysis is, it's not, we don't know that it's good enough, but we also don't suspect it of being faulty or bad. We
yeah,
just don't have the information. And if that's the number one top question that exists and everything else is already proven and it's good, and I've got 2 months to go sort it out, yeah, I'll go do that. It's just that it's, we can't do everything. I think that's the strategy is what are the most important decisions that that program team needs to make? And for example, and you mentioned is, do the reliability testing as early as possible, because if we get the results too late, it's already contracted into the product. It'll cost us a program
yeah,
delay or all these other problems. And if we say this circuit board is bad, it won't last long enough, that may be very expensive to learn late in the program. But and then they'll say, well, we'll ship it anyway. We'll catch up with a revision as soon as we can, and we'll spend a bunch of money on warranty in the meantime. It gets really expensive, but that's why I almost always advocate is that early in the program is working with the engineers in the program is, well, what's the highest risk? What do you need to know so you can choose the right component or right technology or the right vendor or whatever? What are the major decisions you need to have reliability information on? And then let's
yeah.
go build the tests.
No, no, I definitely agree with you. This preventive approach, where you say, "Hey guys, we are developing a new product. Let's discuss openly about what are the main risks." And of
Mm-hmm,
course, there are
mm-hmm.
tools like FMEA, which are definitely helping and raising the awareness within the group.
Yep.
I would also done. I wouldn't neglect also another point, which is to support reliability testing with other elements like field data,
Mm-hmm.
like theoretical investigation. I haven't found anything which is helping to quantify the impact of those information on the confidential level or interval we are going to estimate. That would be something interesting. I think an interesting
Yeah.
research topic. Yeah,
Well, some models do. We know that, say, for example, that capacitor, it has a
yeah,
range of values for its dielectric breakdown. Not every one of them will have a dielectric breakdown at exactly the same voltage. So we know that there's variable there, and then you can work that back through the model for that failure mechanism to account for that uncertainty in it. But its range of variability of when it would fail. So there are ways to back out that if you have really good information about the failure mechanism.
yeah,
But one of the things, going back to that power board you were talking about, and even though it's not the most critical thing, you got two options, I think, to address it so that it's not keeping anybody up at night, but we're also not going to spend a bunch of money chasing it down to the details, is do halt. Just go find out how it fails. And if it fails at the technical well, at the limits that are well beyond our use cases and stresses that it's going to see, we can confidently say it's robust. It's good. Let's go with it. Or it's going to be used in other testing. You need a power to provide it to the other parts of your system, and keep an eye on it. Don't ignore any failures or error messages or anything like that. Keep an eye on it. Put the sensors on it. Monitor it, and look for any anomalies that give you a hint that there may be a problem, and then track them down if anything comes up. It's not ever that part's good, we'll ignore it, even if it has a failure. And I've seen that before, is that it truly has a failure. It was a prototype. No, track it down, understand it. But it's not as rigorous as a full-on life test just for that one system.
Yeah, that's a good perspective also. I think we brought together a lot of different aspects here. So to adopt a preventive approach, forcing the failure as soon as possible. So in the first sample configuration, trying to introducing multiple, let's say, aspect for supporting the statement you are doing about reliability. For example, field data, if there is any field data from previous generation, theoretical modeling, and so on. These are all elements that should be, let's say, integrated in the reliability process. Also, test on component level can help then a statement about sub-assembly level, the step after that. So it's a matter. I wouldn't say so. Testing alone is the solution, but a good testing strategy supported by different elements could be the way, to avoid spending too much time and money, and using in a clever way all the information you can generate by knowing how the product might fail from the present generation, the previous ones.
Man, excellent, Enrico. Excellent summary. It's perfect. And I'm just thinking, if for our listeners, if you're listening to this, did we miss anything? I mean, we just did a quick cut through this, but is there, well, I know one thing that we missed, and we'll have to come back and talk about it some other time, is what happens when your customer requires a particular test?
Yeah, that's another.
Or regulatory tests that are required just to be in the market. What do you do about those? And so there's other aspects that we end up having to deal with. But I think the discussion today, Enrico, kind of outlined a pretty solid strategy for approaching it. And I totally agree with your summary. So if you're listening to this, what do you think? Did we miss anything? Is there anything else that needs to be a factor in how do we put together our test strategy, and how we interact with the team and the tool of testing? How do we use it effectively? Let us know. Head over to Ascendo Reliability. I'm sorry, Enrico. I still am struggling.
Ascendo Reliability is good, but I also like your the way you say it.
Okay. Ascendo Reliability and /go/SOR. There's a couple of ways to get in touch with us there. And you can find Enrico and I on LinkedIn and our about pages on the site. So there's plenty of ways for you to get in touch with us and the other hosts of the show. So please let us know what's on your mind, if it's around testing or testing strategy or anything else, dealing with whatever you're working on. We'd love to hear from you and help you out as best we can, and probably do a podcast about it. So Enrico, have a great rest of your day. Thanks so much for bringing this topic up.
Yeah, thank you for the opportunity, Fred.
All right. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.